Welcome to BSc Main Physics, Semester 6, Paper 1, Solid State Physics, and Unit 5, Magnetic Properties of Materials. We are continuing, and today this is class number S60, Quantum Theory of Paramagnetism. Quantum Theory of Paramagnetism from Solid State Physics, Magnetic Properties. So, a paramagnetic substance that we have seen, what is paramagnetism? In the previous class, we have seen what is paramagnetism. Paramagnetism is due to the presence of unpaired electrons in the material. So, most atoms with incompletely filled atomic orbitals are paramagnetic. Although exceptions such as copper exist, due to the spin, due to their spin, the unpaired electrons have a magnetic dipole moment and act like tiny magnets. Paramagnetism is due to the presence of unpaired electrons in the material. So most atoms with incompletely filled atomic orbitals are paramagnetic. Atomic orbitals ഇൻകംപ്ലീറ്റ്ലി ഫിൽഡ് ആണെങ്കിൽ അവ പാരാമാഗ്നറ്റിക് ആയിരിക്കും. അവിടെ അൺപെയ്ഡ് ഇലക്ട്രോൺസ് കാണും. കോപ്പർ ഒരു എക്സെപ്ഷനാണ്. ഡ്യൂ ടു ദിയർ സ്പിൻ അൺപെയ്ഡ് ഇലക്ട്രോൺസ് ഹാവ് എ മാഗ്നറ്റിക് ഡൈപോൾ മൊമെൻറ്റ്. അപ്പോൾ സ്പിൻ മൂലം അൺപെയ്ഡ് ഇലക്ട്രോൺസിന് മാഗ്നറ്റിക് മൊമെൻറ്റ് ഉണ്ടായിരിക്കും. അവയെല്ലാം ടൈനി മാഗ്നറ്റായി പ്രവർത്തിക്കും. ആൻഡ് നൗ വി ക്യാൻ സീ വാട്ട് ഈസ് ദി ഡൈപോൾ മൊമെൻറ്റ്. The magnetic moment of an atom or ion in free space is given by mu is equal to mu h gamma h j. Gamma h j, that is equal to minus g into mu b j minus g into mu b j. Here total angular momentum h j, total angular momentum h j is equal to orbital angular momentum, and h L is spin angular momentum, that is h s. Total angular momentum is h j, orbital angular momentum is h L, plus the spin angular momentum h s. The total angular momentum is h j. It is equal to sum of h L and h s. H L is the orbital angular momentum and h s is the spin angular momentum. The ratio of the magnitude of mu to that of j is called gyrometric ratio gamma. Gyrometric ratio gamma or magnetogyric ratio. Magnetogyric ratio, mu b is the Bohr magneton. It is defined as EH by 2m. Actually, it is EH by 4 pi m, and when we write in terms of H hat, the Bohr magneton is EH by 2m. For a free atom, the G factor is given by the Lande equation. The G factor is given by the Lande equation, Lande G factor. That is G is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L is missing there, you have to add minus L into L plus 1 all by 2J into J plus 1. The Lande G factor is given by 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1. L is missing, L into L plus 1 all by 2J into J plus 1. This is the Lande G factor, and here L is the orbital quantum number total, S is spin quantum number, and J is the total angular momentum quantum number. For electron spin, G is equal to, the Lally G factor G is equal to 2.00. The energy levels of the system in a magnetic field are U is equal to minus mu dot B is equal to mj G mu B into B. Mj is azimuthal quantum number, or it is the magnetic total angular momentum quantum number. G is the Lally G factor, mu B is the Bohr magneton, and B is the field. Here mj is the azimuthal quantum number. Mj is equal to mj can has 2j plus 1 values. Mj can have 2j plus 1 values, and they are j into j minus 1 plus etc. J minus 1 etc. minus j. For a single spin with no orbital moment, we have mj is equal to plus or minus half, rg is 2, hence u is equal to plus or minus mu b into b. Mu b into b. And the energy distribution is shown in the figure here. In the figure, the ms values 1 by 2 minus 1 by 2 are represented. 1 by 2 and ms values, magnetic spin quantum number, ms values are represented half and minus half, and the two split levels of energy are shown, mu b and minus mu b. The differences are mu 0b and mu 0b, the split difference 2 mu 0b is given. Thus, an energy difference exists between spin magnetic dipole moments parallel and anti-parallel to the field. The magnitude of energy difference is given by 2 mu b into b. It is mu b into b. You look here, in the figure it is mu b into b, not mu is 0. This splitting is shown in the figure. Right side mu b into b. Model plus mu b into b, third minus mu b into b, but difference 2 mu b into b എന്ന് കിട്ടും. And that splitting is shown in the figure. Let us suppose that in unit volume of the paramagnetic material, there is a total number of n atoms. Paramagnetic unit volume n atoms ഉണ്ടെന്ന് വിചാരിക്കുക, n atoms. Then the moments, magnetic moments, that the spin moments of n1 atoms are parallel to the field and n2 atoms are anti-parallel. If a system has only two levels of equilibrium, populations are n1 and n2. ഇപ്പോൾ 2 ലെവലേ ഉള്ളു, അവിടെ ഇക്വിലിബ്രിയം പോപ്പുലേഷൻ ആറ്റത്തിൻ്റെ n1 n2 ആണെങ്കിൽ ഒരു സ്റ്റാറ്റിസ്റ്റിക്കൽ മെക്കാനിക്കൽ ഫോർമുലയുണ്ട്. അതിന് നമ്മൾ ടോ എന്നൊരു ഫാക്ടർ ആദ്യം ഡിഫൈൻ ചെയ്യണം. ടോ ഈസ് ഈക്വൽ കെ ബി ഇൻറ്റു ടി. Tau is Kb into T. Kb is the Boltzmann's constant. T is absolute temperature. Then the number of atoms in the two levels are given by, in a ratio manner, it is given by n1 by n is equal to. This is from the Fermi-Dirac distribution function. And here we write n1 by n is equal to e raised to mu b by tau by e raised to mu b by tau plus e raised to minus mu b by tau. That is n1 by n. And similarly, n2 by n is e raised to, exponential means e raised to minus mu b by tau by e raised to mu b by tau plus e raised to minus mu b by tau. In all cases, tau is taken as kbt, Boltzmann's constant to temperature. And this population of the atoms are shown in the graph. You see the graph. In the graph, x-axis we have taken mu b into by kb into t. The y-axis we have taken the fractional population. The fractional population we have taken. The upper stage and the lower stage are shown here. Now n1 and n2 are the populations of the lower and upper levels, and n is n1 plus n2 is the total number of atoms. The fractional populations are shown in the figure. ആ ഫിഗറിൽ കാണുന്ന ഫ്രാക്ഷണൽ പോപ്പുലേഷനാണ് എക്സ് ആക്സിൽ നമ്മൾ എടുത്തിരിക്കുന്നത്. മ്യൂ ബി ബൈ കെ ബി ടി ആണ് എടുത്തിരിക്കുന്നത്. The production of the magnetic moment of the upper state along the field direction is minus mu, and of lower state is mu. The resultant magnetization for n atoms per unit volume is capital M. That is magnetization. Magnetization is given by n1 minus n2 into mu is equal to n mu into e raised to x minus e raised to minus x by e raised to x plus e raised to minus x is equal to, that we write as n mu tan hx. N mu tan hx, equation number 7. Here x is mu b by kb into t. For x much less than 1, tan hx is approximates to x. Then we have we have repeated here, m is equal to magnetization is equal to n mu, number of atoms, into mu, magnetic moment, into mu b by kb into t. Mu b, that b suffix, mu b by kt, that inside the bracket you have to write mu b suffix. In a magnetic field, an atom with angular momentum quantum number j has 2j plus 1 equally spaced energy levels. The magnetization is given by m is equal to ng j mu b into a function bjx. Here x equal to g j mu b into b by kbt. Equation number 10. What is equation number 10? The value of m. Value of m is equation number 10. Ng j mu b into bjx. That is equation number 10. And equation number 11 is x is equal to g j mu b by kt. Equation number 10 is called Curie-Brillouin law. And bjx is called Brillouin fraction. Brillouin fraction defined as. But Brillouin fraction നമ്മൾ ഇനി പറയുന്ന രീതിയിൽ ഡിഫൈൻ ചെയ്യും. Defined as bjx is equal to 2j plus 1 by 2j cotangent cot h hyperbolic function cot h 2j plus 1 into x by 2j equal 1 by 2j cot h x by 2j. Equation number 7 previously we have seen, just above we have seen. Equation 7 is a special case of equation 12 for j is equal to 1 by 2. Figure 49.3, in the next image we can see, shows a plot of magnetic moment versus the quantity is not clear. It is in the graph we can see. This is the graph. In the graph we have taken in the x-axis. In the x-axis b by t in kilo Gauss per degree is taken. In the y-axis magnetic moment is taken. The y-axis, that is Bohr magnetization is taken on the y-axis. The x-axis b by t in kilo Gauss per degree is taken. So that is the value here. Figure 49.3 shows the plot of magnetic moment versus b by t for spherical samples and samples of 1 potassium, chromium, iron, 2 ferric ammonium, alum, and 3 gadolinium sulfate sulfate hydrate, gadolinium, I shall correct it. Number 3 is gadolinium sulfate octahydrate. Number 3, the figure 49.3, just below we have seen it, shows the plot of magnetic moment versus B by T for spherical samples of 1, potassium, chromium, alum, 2, ferric ammonium, alum, and 3, gadolinium sulfate octahydrate. For x much less than 1, we have cot hx is equal to 1 by x plus x by 3 minus s cubed by 45 plus etc. In that case, what will happen? These are the curve that we have seen. The susceptibility per unit volume is chi equal to m by b. A by b is equal to nj into j plus 1 g square bb square by 3 kbt equal to np square. A new term is coming. np square bb square by 3 kbt is equal to c by t. Here p is called effective number of Bohr magnetrons. Effective number of Bohr magnetrons. It is given by p is equal to g into j plus 1 raised to 1 by 2. So this equation number, the last one equation, chi is equal to m by b equal to nj into j plus 1 g square mu g square by 3 kbt equal to np square mu b square by 3 kbt c by t. That is an important equation. That is a curious equation. Here here p is called the effective number of Bohr magnetrons. It is defined as p is equal to g into j plus 1 raised to 2 by 1 by 2. Equation number 14, the above equation is called a Curie law. C is called a Curie's constant. Thus, we have reached the magnetic susceptibility of a paramagnetic substance by quantum theory. So here, a number of steps we have to remember the values. The continuous derivation is not possible in this small time. So we have to remember some of the equations to write the value of chi, the quantum theory of paramagnetism. The question is discuss the quantum theory of paramagnetism. Discuss the quantum theory of paramagnetism is the question. With this, the 16th class is over. We continue in the next class. Thank you very much.